All right. Well, good morning, everybody. Uh, I did take a look at the calendar and I realized we have this week, we have next week, and then we have finals. So not a whole lot of stuff left, not a whole lot of time left, but we are going to cover a few things. What we're going to cover this week is nuclear chemistry, and next week we will do organic and biochemistry. Okay, so we're not going to learn organic and biochemistry. I'm going to introduce you to a few very important topics in organic and biochemistry, just so that you have an idea of what's going on. I also have had people ask questions about the take-home exam. I did go ahead and delay that for those who had a chance to, who might have trouble uploading something. So I extended the deadline by about an hour or so. So you have a little bit of time after class if you haven't gotten that in to get it in on time. That being said, you might be wondering why I ask for PDF files on that. A lot of you are taking pictures with your phones and just submitting them, and that was fine. The problem is that even though I can read all of those, like when I was grading the test on Friday, I spent more time downloading files, opening files, and everything that I did actually grading it. But if it's a PDF, it will pull up right into the Canvas system, and I can do that. If you can't get that done, that's okay. But if you can, that will save me a fair amount of time and allow me to get grading done a little bit faster. So with that, we need to look at chapter 25. So chapter 25 is where we're going to go next. And the first thing I'm going to ask you to do is to remember chapter 14. Chapter 14 are kinetics, okay? And when we were dealing with kinetics, we had zero order, first order, second order, third order. Before I forget to say it, nuclear kinetics are all first order. So we're going to look at some radioactive decay, and we're going to look at some other things, but all of the kinetics are first order. So we've already learned that. We'll cover it again. I don't know if I'll get to it today or Wednesday, but we're going to spend some time reviewing that. So in addition to getting to cover nuclear chemistry, we are also going to go back through and review some things. Now, while we're at it, let's review a few of the simple things here. Now, whenever we have an atom, we have two different regions of the atom. We have the nucleus and the electron cloud. And often we draw some kind of picture like that. Okay, so here's this nucleus, which is way larger than you would actually see it. Okay, so if I were to draw it to scale, there, you see that little black dot in the middle? No, that's how small the nucleus is compared to the rest of the atom, okay? But when we look at it, the nucleus is really two particles that we're going to focus on. We're going to focus on the protons and the neutrons. Although, amazingly enough, the electron plays a very important part to the nucleus. So we're going to start by looking at something called radioactive decay. Now, radioactive decay is when an atom starts breaking apart, and it gives off something called radioactivity. One of the first people to study radioactivity was Marie Curie. I'm not going to spend a lot of time talking about her, although some of the work she did was incredible. But the three types of radiation that we're going to start with, well, actually probably should start with a little bit simpler review. Let's take a look at the element carbon. See? Okay. Carbon, if we look on the periodic table, we see that it has 6 protons. And if I have carbon 12, it has 6 protons and 6 neutrons. Okay. So this number that goes down here, 6, is the atomic number. This number that goes up here is the mass number. If we put a number up here, it's the charge. If we put something down here that's like the 2 in H2O, that tells you the number of atoms there. Now this is going to be important because we're going to use the same notation for radiation and for nuclear particles, okay? So the 3 radioactive particles we're going to look at are alpha, beta, and gamma radiation. Okay, They're all three things that we're going to see in radioactive decay. Now, an alpha particle is really simple. An alpha particle has an atomic number of 2 and a mass number of 4. And I know that you're thinking, oh, hey, that's helium. Okay. Now, technically, an alpha particle doesn't have the electrons with it, although it will pick up electrons as it goes. So we generally call this, but it's also a helium nuclide. Okay. That's an alpha particle. Okay. A beta particle has an atomic number of -1. And you're thinking, how can it have a -1? Well, it's even better. The mass number is 0. And you might think of that, hey, wow, that's kind of like an electron, right? So the alpha particle is going to have a +2 charge. The beta particle is going to have a -1 charge. And the gamma radiation is just energy. It's the same type of energy we see in the light, okay? Except for it's a little bit more energetic. If you remember the electromagnetic spectrum, at the very, very low energy end, we have radio waves. And those are waves that are like longer than you can see on this screen, okay? Those are radio waves. And then as you get shorter and shorter, between 400 and 700 nanometers, we get to visible light. And if you get shorter than that, it's ultraviolet radiation. And significantly shorter than that, we have X-rays and gamma rays. Those are the really high energy radiation that we have that is given off. And these are the three types of radioactive decay that we're going to see. Now, how do these work? How does it work with a nuclear reaction? Okay, because what we're looking at are reactions where the nucleus changes. Remember when we first started studying the atom in Gen Chem 1, we looked at the Dalton, John Dalton and his theory of the atom. And his first theory was that atoms are, indissoluble. They can't be broken apart. And then, 100 years later, we learned, oh, hey, they can be broken apart. So we had to alter that theory of the atom. The reactions that occur when a nucleus changes are called nuclear reactions. And there's two very simple rules that we have to apply. Okay. First of all, the atomic number has to be conserved. Okay. So between the atomic number on the reactant side and the atomic number on the product side, it's going to be the same. The sum of those numbers will be the same. The same thing is going to happen with the mass number. So the mass number and atomic number need to be conserved. So let's take a look at radioactive decay. Let's look at, say, U-238. Now, I don't have to write down the atomic number, but when I'm doing nuclear reactions, it really makes it a lot easier. And I'm going to look over here at my handy-dandy periodic table that's off the screen. But you might want to look at your periodic table that you have handy. And I see that uranium has an atomic number of 92. It can emit an alpha particle. Or we can put alpha. You can use Ag or alpha interchange. What's the other particle that is given off? Well, I know because the sum of my mass numbers has to be 238. Well, 4 plus 234 is 238. And if this is 92 and this is 2, that has to be 90. And what element has an atomic number of 90? We look at our handy-dandy periodic table. We see that this is thorium. Pretty cool, huh? It's really simple. One of the things that you're going to be doing, and yes, we do have a quiz again this Friday. Yes, this Friday's quiz is going to be all multiple choice. It will actually cover both chapters 19 and 25. So I will give you a little bit of details about chapter 25 on Wednesday on what we need to be able to cover. But a significant number of them are just going to be simply, if I give you, for example, the alpha decay of U-238, what's the other particle? you should be able to determine that. Okay. Other things that we could have that are involved. Okay. So let me introduce a couple other things. We have a beta particle that's negative. Its atomic number is a -1. There is an antiparticle that we call a positron. And a positron is an antiparticle to an electron. If a positron and an electron actually come in contact, they're going to annihilate each other and convert to energy. And I know you're thinking, energy, mass. Remember this equation? I know we didn't cover it in class yet, but you've probably seen this equation. This is the equation you probably have seen outside of science classes more than any other equation. But what exactly does it mean? Well, in any nuclear reaction, there can be a conversion between mass and energy. And some of the mass is often converted into energy. This is where the gamma radiation comes from. Some of the mass is lost and is converted into high energy radiation. Now, the amount of energy that we get depends on the mass that's lost. Now, if I have a reaction, such as this reaction, well, let's go back to the same one we had. Okay, this reaction is also going to give a small amount of gamma radiation off as well. Now, if I find the mass of each of these particles to like the 8th or 9th significant figure, we're going to find a very, very small difference there. That difference in those energies is called a mass defect. And if we have less energy in the products, what happens is that energy is converted, or that energy is produced by the conversion of mass to energy. Okay. This is one of the important things that we're going to do. We're not actually going to spend a lot of time calculating it. This is a fairly simple calculation. See the speed of light, we should remember that from Gen Chem 1, 3 times 10 to the 8th meters per second. And I know if you square that, you get a pretty big number, even with a small mass. So a very small mass can be converted into a fairly large amount of energy. That's important. This is where our nuclear energy comes from. Okay. So really simple things that we have the ability to calculate give huge amounts of energy. Okay. We'll talk a little bit more about alpha, beta, and gamma particles here, because I think it's important for us to understand something. Now, we hear about radiation and we hear about how deadly radioactive substances can be. And this is true. Radiation can do a lot of damage. Now, out of the different pieces of energy that we have, out of the different pieces of radioactivity that we have, they have different amounts of damage they can do. Now, what's interesting is that the alpha particle, out of all of them, does the most damage. Okay? So if you have something that emits alpha particles, it can do a lot of damage to human tissue really quickly. Now, the nice thing about it is because we're talking about helium nuclei, it doesn't take much to block them. This shirt here is enough to block alpha radiation, okay? So are you thinking, oh, well, I don't have to worry about it too much. Well, if you happen to have alpha radiation in the air and you inhale it, there is nothing to keep it from doing damage to you. Or if you were to ingest it, the alpha radiation is going to be really bad. It can do a lot of damage. Now, beta radiation is a little bit less damaging. Okay, well, actually, it's significantly lighter, so it's less damaging, but it takes a bit more to block it. Now, if I wanted to, I could block almost all of the gamma radiation, almost all of the beta radiation by something like the book here. It would block almost all of it. Okay, so it doesn't take that much to block beta radiation, but it takes more. I mean, this shirt would not completely protect me against electrons flying around. Okay, that can be done. Okay, finally, we have the gamma radiation. Now, gamma radiation is basically considered any electromagnetic wave that is strong enough to ionize things, basically to strip electrons off of things. Okay, that's ionizing radiation. The thing about gamma radiation is that it doesn't really do that much damage compared to an alpha particle. But if I want to block the gamma radiation, this shirt is going to do nothing for it. As a matter of fact, if we had 3 feet of lead, that gamma radiation is only going to block about 98%, 98, 99% of that. Okay. So this is very hard to block, even though it does less damage for the amount of energy we have. It does a huge amount of damage because we can't block it. Okay. And the amount of radiation that we have and absorb is going to be important. I'll talk about the units of radiation on Wednesday, and a lot of that has to do with things that people who are working, for example, if somebody is working at as a radiation technologist, they're going to be exposed to radiation on a fairly large basis. This is why if you ever get an X-ray taken, those rad techs, they go into the other room. You're getting a dose of radiation, but you're getting 1, maybe 2 or 3 if you're getting X-rays. Imagine somebody who does hundreds of X-rays in a week. They're getting a huge dose of radiation. And generally they wear something called a film badge and a dosimeter. Those 2 things are going to track the amount of alpha, beta, and gamma radiation that they are exposed to. And if they get exposed to too much, they're done. All right. So, a lot more important things to cover, as in not that they're more important, but there are more also important things that we need to cover with this. Okay. A few other types of radiation that we need to be able to do calculations with. Let's take a look, for example. Now, sometimes the nucleus can spontaneously decay by emitting an electron out of the nucleus. When it does that, if an electron is emitted from the nucleus, then a negative charge is taken away. So basically, a neutron breaks down into an electron and a proton. Now, it's not that simple. It's a lot more complicated than that, but we can overly simplify it down to that. Okay, just giving off. All right, so let's look at an example where we have an electron emitted from a nucleus. And let's say we have, let's go with iron, and let's go with like, something like iron 60 or 61. Okay, there's a lot of neutrons in there. Now, if I look at iron, if I want to know the number of electrons it has, it only has 26. So if I had something that was basically had too many neutrons in it, most likely this is going to undergo a factor decay. Now, in this particular case, what are our numbers? Well, I still have 61, because 61 plus 0 is 61. But what is my atomic number? Well, my atomic number is going to change to 27. It actually goes up. And this gives us cobalt. So what's happened is I have come up with something that's more stable by emitting an electron from the nucleus. Okay, it gives off a beta particle. Now, this is probably still not that stable, but you get the idea that it's become more stable. Now, the question is, what is the ratio of protons to neutrons that's stable in a nucleus? If we look at the very small atoms, we find that, like, for example, oxygen, um, 8 protons, 8 neutrons. Carbon, very stable one, 6 protons, 6 neutrons. So for very small atoms, the ratio of protons to neutrons of 1 to 1 tends to be really stable. Now, as you get more and more protons, somehow or another, you know, we have this idea that positive charges, if I have 2 positive charges, they're going to repel each other. Now, by adding neutrons in there, the forces that hold the nucleus together are stronger than the repulsion of the protons. Now, the forces that hold the nucleus together have been given a very creative name by physicists. They call those strong forces. Okay, so maybe that's not so creative, but it's very clear. Now, the nature of those strong forces, if you really want to talk about that, find yourself a nuclear physicist, talk about that, and they will go through all kinds of theories and everything and tell you about how they're testing it with nuclear colliders and everything. And they spend like 1/10 of a second gathering data, and then 2 to 3 years interpreting it, and then they gather data again. This is the type of thing that we're looking at. We really don't know all the details of the nucleus. Particle physicists think they are near breakthroughs on understanding what's going on at that. I remember talking to a nuclear physicist, and he actually had won a Nobel Prize in nuclear physics. And when I was talking to him, okay, so I say I talked to him. There was like me and like 60 other people who were talking to him. He was just doing a little neat. And I'm not the one who asked the question, but he's like, you know, he went into nuclear physics because he thought that the math and everything, that the particles were small enough, he might actually be able to understand what's going on. When we start looking at chemistry and when we have the attraction of electrons and protons and their interactions, if we were to actually calculate all of those interactions, it would get very, very complicated very quickly. We can simplify it and just look at the effects of those interactions. But his point is that if I can just get to the small enough particles, I can calculate all of those interactions. So I said, so how close are you to doing that? He says, well, now, I was a college student when he did this. And he's like, your students may have a chance. And he didn't say, you might have a chance. Your students might have a chance. So it's your generation that he thinks is the very first one that might really be able to understand what's going on a nuclear level. Okay. Simple things. Now, there's another kind of reaction that can occur, and I'm going to throw one out here, and that is electron capture. There are times when the electron is actually on the, how do I know if something's considered stable? I will let you know here in a minute. Okay, I want to show you the electron capture first before I go through that. So what if we have something like, and I'm going to use the iron example again, and what if I have like iron 52? Very neutron deficient. Sometimes what can happen is, now this is again going to be 52, and my number here is now going to be, since this is 0 and -1, 25. And I now have some manganese here. Now the question is, how do we know? Oh, let's see. I got to read this one. I can see men walking in slightly late to the collider with a Starbucks cup in his hand. Yes, I can see that. And remember that the data collection of the collider is like fractions of a second. So he would like miss the entire thing and just get it on the data. However, you wouldn't know that you saw anything until 2 years later anyway. So that would be normal. All right. That was a good one. Hopefully everyone saw that on the chat. How do we know if something is stable? if you take a look in your book at page 982, you will see a stability of atomic nuclei. And what they've done is they have plotted the stable nuclei of number of neutrons on the y-axis and number of protons on the x-axis. And what you see generically is that if this is 1-to-1, we will see that, you know, for very small particles, a 1-to-1 ratio is there. And again, it's dead. All right. You're going to see that that ratio goes up, and eventually that ratio ends up at about 1.5 to 1. Okay. So how do we know which nuclei are going to be stable? We have looked at nuclei and found which ones are stable. Okay. So again, we don't really have a calculation that can tell us, but we have a pretty good idea of the ratio of neutrons to protons for different areas. The other thing that we found out is that there are also a stability of nuclei based on the size. The most stable nuclei are iron 59 or somewhere in that area, somewhere around iron. So in case you're wondering what kind of nuclear reaction is likely to occur, if you have small molecules, they're more likely to fuse together. If you have large molecules, they're more likely to break apart. Now, those types of reactions that we have, if nuclei come together to form it must be Monday. Coffee time for a second. Not coffee time for a second. All right. Can't make coffee and can't drink coffee if I don't have it. All right. So let me go back to this. See if I can say this without confusing myself here. More importantly, not splitting my tongue. If I take small atoms and I put them together, small nuclei, put them together to get larger nuclei, that's fusion. If I take large nuclei and I split them into smaller nuclei, that's fission. Okay? So in case you're wondering, we get most of our energy from fusion. And I know you're thinking, but the nuclear power plants all use fission. Yes, the nuclear energy that we control, where we have a nuclear power plant, all occurs with a fission reaction. But the big sun, that big bright ball of nuclear reaction in the sky, that is a reaction of hydrogen fusing to helium, and even some larger things eventually. But that reaction that occurs in the star is all fusion. And one of the fun things is that somebody was saying, well, what happens if we could actually harness that energy of hydrogens fusing together? And well, we can, but it gets kind of warm. So they thought, well, what if we did it at a lower temperature? What if we could do it at a controllable temperature, fusion at a controllable temperature? And this is one of those, it's kind of like the Philosopher's Stone. You know, if we could do it, we could do all kinds of things that we don't think is possible now. What's funny is when I was in college, there was actually a group who came out with cold fusion where they were gaining energy at fairly close to room temperatures. And it was reported in the news and everything like that. And it turns out that their data was just off. They did a mistake in calculations. So this is one of the fun things. This is why you have somebody look over your work before you try to publish it or go to the news and say, oh, this happens. You look at that. The joke is that, well, the reason they got that is they had a few too many drinks before they did the lab. Okay, I don't know whether that's true or not. That's a rumor that I heard. The guys doing that were not completely sober when they were doing this reaction or doing the calculations. And they came up with more energy than they started with. And it's like, we have cold fusion. So in the scientific circles, if you hear jokes about cold fusion, this is usually happens when somebody reports something to the press before going through their peers. If you report it to the press first and then you go through your peers and your peers all find out, you messed up. Okay, that's not what it is. So that's one of the fun things about this. And we're not going to really cover it in this class, but peer review is really important. Having somebody else look at your work and see, does your conclusion that you're coming out of this make sense? Now, what's interesting is that there are times where the conclusion is not right, but it still makes sense. But we don't find out it's not right until years and years later. So if you look at papers from like 60 or 70 years ago, they may have things in there that we have now since found that they're wrong. That doesn't mean that that paper wasn't good. A lot of times the study of those results lead to more and more knowledge. And eventually we may find out, okay, we've been assuming that this was the way everything was working for 10, 15 years. And after doing more and more intense study of it, we figure out that's not right. That's okay. That doesn't invalidate somebody's research. Now, things that do invalidate somebody's research is, putting data in there that's not accurate, or calculations that do not arise, that are not correct for the data that you have. Sticking false data in there is wrong. That causes a lot of problems. Okay. First of all, that if you are reporting your actual data and somebody else tries to replicate it and they get different data, that's one thing. If you are making up the data, that's different. That is dishonesty, and that causes a lot of problems. And you can actually set science back generations by making up data. We don't want to do that, okay? It's better to take and say, all right, this is not the data that I was expecting, but it's what we're going to report. There have been a few cases where people reporting climate data didn't like the trends that they were seeing, so they added some other data in there to make the trend work a lot better. That's bad. Okay. Now, if you really want to understand what's going on with the climate, you want accurate data. And even if it's not showing what you think it is, even if it's like, oh no, the politicians aren't going to believe me now because my data is showing a little trend, you've got to stick with the truth. Instead of that, now there are a lot of people who are saying, well, there was falsified data used for some of the climate research, therefore, why should we believe any of it? So somebody, by making up data, has now validated people's skepticism, when in reality, had they just reported the data, I think we would have learned a lot more from it. Just a little bit of lesson of science there. All right, back to a little bit of nuclear chemistry, and then I'm going to stop, and then we'll go from there. Okay. All right. Let's look at something. Okay, and I am going to go back to uranium, and we're going to go from uranium 238. And there are a series of reactions that can occur. Okay, and this series of reactions is quite fun, but eventually, after a number of reactions, we get down to lead-206. Okay, now what's interesting about this is the only place we've ever encountered lead-206 is in the same things where we see some uranium. Any other lead that we see is not lead-206. So the assumption is made that all of that lead is a daughter product of the uranium, okay? And because this uranium is decaying to lead-206, if we know the amount of uranium we have, and we know the amount of lead we have. So let's say, for example, we have, equal amount of these. We could say that initially we had twice as much uranium and 0 lead. And now through decay, we have half the amount of uranium. So basically, in that case, 1 half-life has occurred. Now, hopefully, you did the data with the half-life. If you haven't, it's due this week. But with a half-life, we see that the amount of time that it takes for half of something to decay is consistent for a particular reaction. So the decay of U-238 to lead-206 allows us to look at the age of something that has this in here. And with this radioactive dating, we're able to determine things. Okay? One of the things they've been able to estimate the age of is the Earth. Now, when I was a student, okay, when I was sitting in general chemistry, they said the Earth is about 4 billion years old. And our data today shows that the Earth is 4.55 billion years old. You didn't realize I was that old, did you? Okay. So again, what happened is that they were able to refine some measurements and find more, some different rocks to be able to do radioactive dating with. And they're able to do this. We'll look at how that works. But before that, I want to look at one more. Okay. We're going to look at carbon dating. Okay. Now, carbon dating is based on carbon-14. Okay. And carbon-14 occurs, and let me see if I can tell you what page we're on in here in the book. So this is the radiocarbon dating you'll find on a page, about page 990, 991. Again, if we look at that, there is a certain reaction that is going to give us carbon-14. And that's a reaction of nitrogen and this gives us this reaction occurs in the atmosphere, okay? And it's a fairly constant reaction. So the amount of carbon-14 in the atmosphere is relatively constant. And this carbon in the atmosphere generally reacts with oxygen and we get CO2. And what happens with plants? They pull CO2 out of the air, okay? Getting CO2, that's pretty simple. Living things constantly replenish their CO2. So a living thing is going to have an amount of carbon-14. Now, this carbon-14 is actually going to radioactively decay. Yeah, they don't show the reaction of it. But the radioactive decay of carbon-14, what I'm looking for is a half-life. I should have this memorized. Uh-oh. All right. There is an Amber Alert. You guys probably might have gotten that one too if you have those crazy things. That alarm. I was worried that was going to be some weather. But carbon-14 has a half-life of about, I should have this memorized. I should have looked it up. 5,730 years. Okay. So if I look at the amount of carbon-14 that we have currently and the amount of carbon-14 that we have in something that is no longer living. Now, once a tree stops living, and as long as it's living, it's going to be constantly going through photosynthesis, pulling CO2 out of the air, giving off oxygen. The amount of carbon-14 is constant in there. Okay. As it decays, the amount of carbon-14 is going to go down. And we can actually measure that. Now, let me simplify. Now, often, we use the form of the equation, and you will find this on page 989. And we also know that the natural logarithm can be used to find this. So the half-life is 0.693 over K. All right. Now, I want you to do something for me. Let us say that we have something and let's see if I have the data here. Now, I'm making this data up, but I'm going to give you a realistic chance to calculate it. Now, one of the things that can be measured is in addition to finding the number of particles that are originally there, we can actually look at the activity of it. And let's say for a currently living thing, the activity is 6,400 decays per second. Okay, and I have something that has an age of, or if I look at it, it's like made of wood and it's fairly old. We'll see what it is. But if I measure it, it's got like 2,100. How old is that going to be? Okay, well, because it's first order, the units don't matter here. Okay, now the half-life, T1/2, with that, you can calculate that. And I am going to actually pause my recording and I'm going to have you guys calculate. Okay. All right. So I just put the recording back on. So I'm going to repeat that. If I go through this calculation, I find that I end up with that 9,286 years. All right. With that, I am going to have to stop and take a break for a second. I am going to return and we'll do some office hours so you can ask me all kinds of questions for that. But I need to take a break for just a minute before we do that. So with that, I will end class for the day.